Every year, millions of people stand at the rim of the Grand Canyon and look down. They see the canyon walls dropping away beneath them in a series of broad, stepped terraces, each one a different color, a different texture, a different shade of red or cream or gray or purple, depending on the hour and the season and the particular quality of the light. They see the Colorado River far below, moving quietly through the inner gorge like a silver thread drawn through the base of a stone cathedral. They see the sky above, enormous and blue, and the far rim of the canyon miles away across the open air. And most of them, after standing there for a while, feel that they have understood something important about this place. But what if the canyon we see from the rim is only the most recent chapter in a story so long that it makes the entire span of human history seem brief by comparison? What if the cliffs and the river and the colored layers of stone are not simply a dramatic landscape, but a record, a physical archive of worlds that no longer exist, preserved in the rock beneath our feet and the walls rising around us? What really lies beneath the Grand Canyon? That question sounds simple. It sounds like it might have one answer, something hidden, something dramatic, something waiting to be revealed. But the more carefully you follow that question down through the geology and the archaeology and the history of this place, the more you realize that the answer is not one thing. It is many things. It is ancient seas and vanished deserts and living rivers and underground water and fossils and archaeological sites and thousands of years of human knowledge and half a dozen genuine scientific debates that have not yet been resolved. The Grand Canyon is one of the most studied places on Earth, and yet it still holds questions that geologists and archaeologists and hydrologists and ecologists have not fully answered. Not because anyone is hiding the answers, but because the canyon is genuinely that complex, genuinely that old, genuinely that deep. Tonight, we are going to follow that question wherever it leads. Down through the rock layers, back through geological time, beneath the visible surface of the landscape, into the hidden world of underground water and natural caves and fossil ecosystems. We are going to explore the human history of the canyon, a history that reaches back thousands of years before the first European explorers arrived on the rim. And we are going to sit with the questions that modern science has not yet fully answered, because those questions are not a failure of knowledge. They are an invitation to keep looking. If quiet journeys through America's ancient landscapes are your kind of history, consider subscribing to History's Sleepy Time. New documentaries arrive regularly, and every one of them is designed to carry you slowly through time. Now, let us follow this question all the way down. The canyon you see is real, but the world beneath it is far older, far stranger, and far more remarkable than anything visible from the rim. To understand what lies beneath the Grand Canyon, we have to go back to a time before there was any canyon here at all. A time when this entire region looked nothing like the landscape we know. A time so remote that the human mind can only approach it gradually, the way your eyes slowly adjust to darkness. The story begins much further back than most people expect. There is a particular difficulty in imagining deep geological time. Human beings are reasonably good at imagining decades, and we can stretch our minds to encompass centuries if we work at it. 1,000 years is difficult but possible. 10,000 years pushes the boundary of what our imaginations can genuinely hold. But 1,000,000 years is something different entirely. And 1,000,000,000 years is almost beyond comprehension, a span of time so enormous that even the oldest human civilizations occupy only a tiny fraction of its final moments. The Grand Canyon reaches down through approximately 2 billion years of Earth's history. The rocks at the very bottom of the inner gorge are among the oldest exposed rocks on the surface of the planet, ancient beyond any ordinary sense of the word. And the landscape that exists there today, the canyon itself with its layered walls and its river and its desert climate, is in geological terms quite recent. The canyon, as we know, it began forming perhaps 5 to 6 million years ago, and possibly even more recently than that, depending on which scientific interpretation you follow. But before the canyon, this region had already lived through an almost unimaginable succession of different worlds. At various points over the past 1.5 billion years, the land that is now the Colorado Plateau was covered by shallow tropical seas. Then it was dry coastal flats. Then it was deep ocean. Then it was river deltas and wetlands. Then it was vast sand dune deserts, larger than the Sahara. Then seas again. Then coastal environments. Then the region was pushed upward by geological forces, and the rivers that crossed it began cutting downward through the accumulated rock layers, slowly exposing the record of everything that had come before. The landscape changed not once or twice, but dozens of times, shifting through different environments over hundreds of millions of years in response to forces that operated on a scale that dwarfs anything in recorded human history. What drove all of this change? The movement of continents plays a central role. The region that is now the American Southwest has not always occupied its current position on the globe. Over geological time, the North American continent has moved northward from positions closer to the equator, carrying the rocks of the Colorado Plateau with it. Environments that exist in the tropics today, warm shallow seas, lush coastal swamps, vast sand deserts, once covered this region because this region was in the tropics. The rock layers of the Grand Canyon are partly a record of that long northward journey. Volcanic activity, the building and erosion of mountain ranges, the rise and fall of sea levels driven by climate change, all of these forces contributed to the succession of environments preserved in the canyon's walls. The rock layers are not simply decorative striations. Each one is a document written in sediment and chemistry and the traces of organisms that lived and died in a world that no longer exists. But to read that document, we have to start at the very bottom. We have to go to the oldest rocks, the ones that lie beneath everything else, the ones that were already ancient when the familiar canyon layers were first being deposited. What lives at the bottom of the Grand Canyon's geological record is something that takes the breath away, not because it is dramatic in the conventional sense, but because it is so profoundly old. If you could make the long descent from the rim of the Grand Canyon all the way to the Colorado River, following one of the trail systems that wind down through the canyon's successive rock layers, you would notice something change, as you approached the inner gorge. The layers of sedimentary rock that form the canyon's broad upper walls, those familiar bands of red and cream and gray that you can see from the rim, gradually give way to something different as you descend. The rock becomes darker. It becomes more complex in texture, twisted and contorted in ways that sedimentary rock is not, with visible crystals and a quality that is harder to describe than to observe. You are entering an entirely different part of the geological record, one that predates all the familiar canyon layers by an enormous margin. These are the Vishnu Basement Rocks, and they are among the oldest exposed geological formations in North America. The Vishnu Schist, as the most prominent component of this ancient formation is called, has been dated by geologists using radiometric methods to approximately 1.7 to 1.8 billion years ago. To put that in context, the oldest of these rocks formed before the first complex multicellular life appeared on Earth. They formed when the atmosphere itself was different, when the oceans were different in their chemistry, when the continents were arranged in configurations that bear no resemblance to the modern world. These rocks were not sedimentary in origin. They did not form from the accumulation of particles at the bottom of a sea, the way most of the canyon's upper layers did. They formed deep within the Earth's crust, under conditions of enormous heat and pressure, during a period of intense mountain building that geologists call an orogeny. The original rocks, which may have included sedimentary and volcanic materials, were buried miles below the surface of an ancient continent and subjected to heat and pressure intense enough to transform them into the metamorphic rock we see today. The mountain range that was built during this ancient orogeny was, by some estimates, comparable in scale to the modern Himalayas. It has long since been completely eroded away, worn down to its roots over hundreds of millions of years. What we see in the inner gorge of the Grand Canyon are the deep roots of those vanished mountains, exposed by the canyon's subsequent erosion, brought back to the surface after spending more than 1 billion years buried beneath the layers that accumulated above them. Intruding through the Vishnu Schist in visible pink and light-colored veins are rocks called the Zoroaster granite, formed when molten material forced its way up through the older metamorphic rock during ancient periods of geological activity. These granites have been dated to roughly 1.6 to 1.7 billion years ago, somewhat younger than the surrounding schist, but still ancient beyond ordinary comprehension. Standing in the inner gorge of the Grand Canyon and placing your hand against the surface of the Vishnu Schist is one of the more quietly remarkable things a person can do. The rock beneath your fingers was formed when Earth was less than half its current age. Everything that has happened in the biological history of this planet, every organism that has ever lived, every environment that has ever existed, every geological process that has ever operated at the surface, all of it has occurred in the time since these rocks formed. The Vishnu Basement Rocks represent the floor of the Grand Canyon's geological archive. Everything above them was deposited later, much later in some cases, and the transition from the ancient basement to the overlying rock layers is itself a remarkable geological feature. between the Vishnu Basement Rocks and the next major set of rock layers above them. There is what geologists call an unconformity, a gap in the geological record representing an enormous span of time during which either no rock was deposited or rock that was deposited was subsequently eroded away before the next layers accumulated. This particular unconformity in the Grand Canyon represents a gap of perhaps 250 million to 300 million years, a stretch of time during which an entire chapter of Earth's history is simply absent from the local record. Geologists call this particular feature the Great Unconformity, and it is visible in the canyon walls as a dramatic and abrupt boundary between the ancient basement rocks and the much younger sedimentary layers above them. The sheer scale of the missing time represented by that boundary has fascinated geologists since it was first recognized in the 19th century. Research into the processes that created it continues today. Above the Great Unconformity, the canyon's familiar layers begin. And each one of those layers carries its own story about the environments that once existed here. Somewhere around 520 million years ago, the region that is now the Colorado Plateau lay near the edge of an ancient continent, at low elevation, close to sea level, in a warm and shallow marine environment not entirely unlike the shallow coastal seas of the modern tropics. The sea advanced slowly across the land, as seas do when the land is low and the water level rises, depositing layer after layer of sediment on the seafloor as the water deepened. Sands accumulated first, carried by coastal currents and the movement of water across the shallow floor. Then, as the water deepened and the environment changed, finer particles settled from suspension, silts and muds that would eventually be compressed into shale. And in zones where the water was clear and the chemistry was right, calcium carbonate precipitated from the water itself and accumulated in thick deposits of limestone. Those three rock types, sandstone, shale, and limestone, are the primary components of the Grand Canyon's great stack of sedimentary layers, and they tell us that the environments which produced them shifted repeatedly between different marine and coastal conditions over hundreds of millions of years. The Tapat sandstone, one of the first major sedimentary layers above the Great Unconformity, preserves the evidence of that ancient shoreline advance. Its grains are rounded and sorted in ways that indicate they were moved and deposited by water, in currents consistent with a coastal or near-shore marine environment. The Tapats is generally dated to the Cambrian period, roughly 505 to 520 million years ago, a time in Earth's history when multicellular animal life was undergoing one of its most significant and rapid periods of diversification. Above the Tapats lies the Bright Angel Shale, a formation composed largely of fine-grained sediments deposited in somewhat deeper, quieter water. The Bright Angel is one of the most fossil-rich formations in the Grand Canyon, preserving the traces and remains of the marine animals that lived on and in the seafloor during the Cambrian period. Trilobites, ancient arthropods that existed for hundreds of millions of years before their eventual extinction, left their remains in this layer, along with the trace fossils of worms and other organisms that burrowed through the ancient seafloor sediments. Above the Bright Angel lies the Muav limestone, deposited in even deeper water as the sea continued to advance across the continent. The limestone preserves evidence of a clear, warm, carbonate-rich marine environment, the kind of environment that exists today in shallow tropical seas. These three formations together, the Taypats, the Bright Angel, and the Muav, represent a single transgressive sequence, the advance of the sea across what was previously dry land, preserved as a continuous stack of rock, recording the progressive deepening of the water over millions of years. But here is something worth sitting with for a moment. The same rock that forms the trail beneath your feet on a desert hike in Arizona, rock that feels as dry and ancient as anything you have ever touched, was once mud on the floor of a tropical sea. The same canyon walls that glow red in the afternoon desert sun were once covered by water, inhabited by organisms so ancient that they had no connection to any animal group that exists today. The world preserved in those rock layers is not hypothetical. It is not inference in the speculative sense. It is documented in the chemistry of the rock, in the physical structures preserved within it, in the fossils that represent the actual organisms that lived and died in that ancient sea. The evidence is there for anyone who knows how to read it, and reading it is exactly what geologists have spent 2 centuries learning to do. The science of reading rock layers has a formal name: stratigraphy. It is, in its simplest expression, the study of layered rocks as a record of time and environment. The foundational principle of stratigraphy was articulated in the 17th century by the Danish scientist Nicholas Steno, who observed that in any undisturbed sequence of rock layers, the oldest layers lie at the bottom and the youngest at the top. Rock accumulates from below, each new layer deposited on the surface of the previous one, so that reading a sequence of layers from bottom to top is equivalent to reading a sequence of events from oldest to most recent. In the Grand Canyon, that principle operates on a scale that makes the canyon itself a natural geological textbook, one that took the Earth hundreds of millions of years to write. Each layer in the canyon's walls was deposited in a specific environment over a specific period of time. The thickness of each layer reflects roughly how long deposition continued in that environment and how rapidly sediment accumulated. The composition of each layer, whether it is sandstone, shale, or limestone, tells you something about the energy of the depositional environment, whether water was moving rapidly or slowly, whether the organisms that lived there built shells of calcium carbonate, whether the climate was wet or dry. The color of each layer reflects its mineral content. Rocks containing iron oxides tend toward reds and oranges. Rocks with different mineral compositions appear gray or cream or purple. The characteristic banded appearance of the Grand Canyon's walls, visible from miles away, is a direct expression of the changing chemical environments in which the successive layers were deposited. Within each layer, smaller scale structures preserve even more detailed information. Crossbedding, a pattern of diagonal lines within a layer of sandstone, can indicate whether the sand was deposited by wind or water, and in which direction the current was flowing. Ripple marks on ancient bedding surfaces record the movement of water over shallow sandy bottoms that are now preserved as stone. Mud cracks formed when wet sediment dried and contracted at a water's edge are preserved in some layers exactly as they appeared the moment the ancient mud dried and hardened. Fossils, of course, are among the most powerful tools for reading the rock record. The organisms preserved in a rock layer tell you not only about the biology of the ancient environment, but also about its age, because different organisms existed at different periods in Earth's history, and the presence of particular fossil types can constrain the age of the layer that contains them. Modern dating methods, particularly radiometric dating techniques that measure the decay of radioactive isotopes within certain mineral types, have given geologists a way to attach numerical ages to the rock record. Converting the relative sequence of older and younger layers into an absolute chronology measured in millions and billions of years. Together, these tools allow geologists to reconstruct ancient environments with a degree of confidence that surprises many people who have not encountered this work before. When a geologist looks at a particular layer in the Grand Canyon wall and says that it was deposited approximately 300 million years ago in a shallow marine environment during a period of rising sea level, that statement is not guesswork. It is a conclusion supported by physical evidence, chemical analysis, fossil content, and radiometric dating. The rock remembers, and science has developed the language to hear what it is saying, but the environments recorded in the Grand Canyon's layers are not all marine. Not all of them speak of ancient seas. Some of them speak of something entirely different. Run your hand along the surface of the Coconino sandstone, visible as a pale, almost white band in the upper walls of the Grand Canyon, and you will notice something unusual about its internal structure. The rock is cross-bedded, but the crossbeds are large, sweeping curves that dip in consistent directions, and their scale and geometry are unlike anything produced by water. They are the preserved remnants of ancient sand dunes. The Coconino sandstone, deposited roughly 270 to 275 million years ago during the Permian period, represents a vast ancient desert, a dune field that some geologists have estimated may have been comparable in scale to the modern Sahara. The sand grains in the Coconino are rounded and frosted, polished by wind in the way that wind-driven sand polishes grains in a way that water-transporting sand does not. The large-scale crossbedding preserves the advance of individual dune faces across the ancient landscape. The footprints of small tetrapods, four-limbed vertebrates of various kinds, are preserved on ancient dune surfaces within the Coconino, recording the actual movements of living animals across the desert more than 270 million years ago. These trace fossils are not the preserved remains of the animals themselves, but rather the impressions their feet left in the damp surface of a dune slope, impressions that were covered by subsequent sand and eventually lithified into stone. Above the Coconino lies the Toroip Formation, which records a shift back toward coastal and marine environments, a sea advancing again from the west across the desert landscape. And above the toroep is the Kaibab Limestone, the topmost layer of the Grand Canyon's main sedimentary sequence, which forms much of the surface of the canyon's rim today. The Kaibab was deposited in a shallow marine sea that covered the region during the Permian period, a sea rich in marine organisms whose fossils, including sponges, brachiopods, and mollusks, are preserved within it. Beneath the Coconino, moving downward through the canyon's layers, you encounter the Hermit Formation, a brick-red layer of shale and fine sandstone deposited in a coastal and floodplain environment, containing the fossil impressions of ancient plant material and the trackways of early tetrapods moving through a wet lowland landscape. Below the Hermit lies the Supai Group, a thick sequence of red sandstones and shales representing repeated cycles of coastal, river, and tidal flat environments spread across tens of millions of years of deposition. Each of these formations records a different world: desert, sea, coastal plain, river delta, desert again. Sea again. The region cycled through these environments over and over as sea levels rose and fell, as the climate shifted between wet and dry, as the continent moved northward from equatorial positions toward higher latitudes. What drove all of this environmental change? Sea level changes caused by the growth and melting of continental ice sheets played a major role. Climate shifts, driven by changes in atmospheric composition and continental configuration, contributed as well. The movement of the North American continent itself, carrying the region from tropical latitudes northward, gradually changed the range of climates that were possible there. The Grand Canyon's layered walls are, among other things, a record of climate change operating across geological time, not the rapid climate change of human experience, but the slow, cyclical, inexorable climate change driven by forces that operate over millions of years. And beneath all of these layers, beneath the seas and the deserts and the river plains, the Colorado Plateau was slowly building toward its modern form. Something was happening to the land itself, a process of lifting and carving that would eventually create the most spectacular canyon on Earth. For most of the period during which the Grand Canyon's rock layers were being deposited, the region was relatively low-lying, close to sea level, the kind of flat or gently rolling terrain across which seas could advance and retreat, and rivers could meander across broad floodplains. The landscape did not look anything like the canyon country we know today. The transformation began when the Colorado Plateau started to rise. The Colorado Plateau is a large region of the American Southwest, encompassing parts of Arizona, Utah, Colorado, and New Mexico, that is geologically unusual in a specific way. While the regions surrounding it were being deformed, stretched, and fragmented by the tectonic forces that created the Basin and Range Province to the south and west, the Colorado Plateau remained largely intact, a coherent block of older rock that resisted the deformation affecting its surroundings. Instead of stretching and breaking, it rose. Geologists refer to this process as uplift, and while the precise mechanisms that drove the uplift of the Colorado Plateau are still an area of active research and discussion, the general picture is that the plateau began rising significantly sometime in the past, several tens of millions of years, ultimately reaching elevations of roughly 5 to 8,000 feet above sea level in different parts of the region. Elevation matters enormously for erosion. Rivers erode more aggressively when they are flowing at higher elevations, and when their gradient, the steepness of their descent towards sea level, is increased. As the Colorado Plateau rose, the rivers crossing it gained erosional energy, and they began cutting downward through the rock layers beneath them. The Colorado River, which drains a huge area of the western interior of North America, became the primary agent of the canyon's formation. As the river cut downward, it exposed progressively older rock layers, and the process of weathering and erosion of the exposed canyon walls broadened the canyon laterally over time. But the question of exactly when the canyon began forming has been the subject of considerable scientific debate. For many decades, the prevailing view among geologists was that the Grand Canyon was geologically young, perhaps 5 to 6 million years old, carved rapidly by an ancestral Colorado River that integrated its drainage to the Gulf of California relatively recently. This view was supported by various lines of evidence, including the ages of sedimentary deposits downstream that appeared to record the arrival of Colorado River sediment in the basin near the modern Gulf of California. However, research published in the early part of the 21st century proposed a more complex history. Studies using a dating technique called thermochronology, which measures the thermal history of rocks as they are brought toward the surface by erosion, suggested that some parts of what is now the Grand Canyon may have existed as a significant topographic feature much earlier, potentially as far back as 70 million years ago, though this interpretation remains debated. The current scientific picture, which continues to evolve as new data is collected, is that the canyon's history may be complex, with different sections having different ages and potentially involving the integration of older valleys by the modern Colorado River during its relatively recent history. Some researchers speak of an old canyon hypothesis, suggesting that parts of the canyon's western section are considerably older than the eastern sections. Others maintain a young canyon model for the entire feature. What is not in dispute is that the result of all of this geological activity is one of the most remarkable landscapes on the surface of the Earth, a canyon that reaches a mile deep in some places, stretches up to 18 miles across at its widest, and extends for approximately 277 miles along the course of the Colorado River. The process that created this landscape is ongoing. The river continues to flow. The canyon continues to erode, though at rates that are slow by human standards. The canyon is not a finished product. It is a work in progress, shaped by the same forces of water and time that have been operating here for millions of years. And at the center of all of this is the river itself, moving quietly through the deepest part of the canyon it helped to create. There is a particular quality to the sound of the Colorado River in the inner gorge of the Grand Canyon. It does not sound like a gentle stream. In places where rapids occur, and there are many rapids in this section of the river, it fills the canyon with a deep, continuous roar that seems to come from the rock itself, as if the stone were vibrating with the effort of holding back all that moving water. In the calmer stretches between the rapids, the sound softens to a steady, rhythmic rushing, the sound of a large volume of water moving purposefully through a confined space. The Colorado River is, in the simplest geological terms, the primary sculptor of the Grand Canyon. It has been cutting downward through the Colorado Plateau for millions of years, driven by the force of gravity and the energy of the enormous volume of water draining toward it from the mountains of Colorado, Wyoming, and Utah. At its natural peak flows before modern dams altered its regime, the Colorado carried enormous quantities of sediment, silts, sands, gravels, and boulders in suspension and along its bed, and it was this sediment-laden water, essentially a liquid abrasive, that cut most effectively through the rock. The process of river erosion is not simply a matter of water dissolving rock, though chemical dissolution does play a role in certain rock types. It is primarily a mechanical process, the grinding and abrading action of sediment particles being carried against the rock surfaces of the riverbed and banks. The river picks up fragments of rock from the riverbed, carries them downstream, and in doing so uses them as tools to wear away more rock from the surfaces they travel across. Rapids in the Colorado River within the Grand Canyon form primarily where tributary streams have deposited large amounts of debris, boulders, and gravel into the main river channel during flash floods. These debris fans create constrictions that force the river's water through a narrow space, increasing its velocity and turbulence, and creating the white water that rafters and kayakers have been navigating for well over a century. The river carries information downstream. The sediment in the Colorado River is a sample of everything it has eroded from the landscape upstream. The chemistry and mineralogy of those sediments reflects the geology of the watershed. And scientists studying the river's sediment load can learn about the geology of distant regions simply by analyzing what the water is carrying. Before the construction of major dams on the Colorado system in the 20th century, this sediment reached the Gulf of California and was deposited in a large delta, building a landscape at the river's mouth from material gathered across an enormous area of the western interior. The modern Colorado River in the Grand Canyon is considerably different from its pre-dam condition. The Glen Canyon Dam, completed in 1966, immediately upstream of the Grand Canyon National Park, captures most of the river's sediment load before it reaches the canyon. The water released from the dam is clear and cold, lacking the sediment that the natural river would have carried, and that played an important role in shaping the canyon's riverine ecosystem. Water flowing on the surface of the landscape is only part of the story of water in the Grand Canyon system. Some of the water that falls as rain and snow on the plateau above the canyon does not run off the surface at all. It sinks into the rock and begins a slower, hidden journey, one that plays its own role in shaping the landscape beneath our feet. The question then becomes, where does that water go? Rain falls on the south rim of the Grand Canyon, soaks into the pale limestone of the Kaibab Plateau, and disappears. It does not immediately reappear as a stream or a spring on the canyon walls below. It does not rush down the surface of the cliffs, invisible rivulets, the way water moves across impermeable rock. Instead, it moves inward, downward, and sideways through the rock itself, following pathways determined by the porosity and permeability of the geological formations it encounters, traveling routes that are largely invisible to anyone standing above. This is groundwater, and it is one of the most important and least understood aspects of the Grand Canyon's hydrological system. Groundwater is simply water that occupies the spaces within rock and soil beneath the surface. Every rock has some degree of porosity, meaning it contains small spaces between its grains or within its crystal structure that can hold water. But porosity alone does not determine how easily water moves through a rock. Permeability matters equally, and permeability reflects how well connected those spaces are to each other. A rock can have high porosity but low permeability if the spaces within it are isolated from one another, preventing water from moving freely from one to the next. In the Grand Canyon region, the different rock formations have dramatically different hydrological properties. The Kaibab limestone that caps the rim is moderately porous and contains solution cavities, spaces dissolved by slightly acidic groundwater over geological time that allow water to move through it. The Coconino sandstone below the Kaibab is also permeable, allowing water to migrate downward through its sand grains. But other formations, particularly the shales like the Hermit Formation and the Bright Angel Shale, are relatively impermeable, acting as barriers that intercept downward-moving groundwater and redirect it horizontally. This layered arrangement of permeable and impermeable formations creates a complex underground plumbing system within the canyon's walls. Water moving downward through the Coconino sandstone, for example, eventually reaches the relatively impermeable Hermit Shale below it and is deflected laterally, moving sideways through the permeable layer until it finds a pathway to the surface, often emerging as a spring at the contact between the two formations. Springs are among the most significant features of the Grand Canyon's ecological and human geography. In a landscape that receives relatively little precipitation, and where surface water is concentrated almost entirely in the main river channel far below the rim, springs represent critical sources of water for both wildlife and, historically, for human communities navigating the canyon. Some of the Grand Canyon's springs are permanent, flowing year-round from groundwater reservoirs that are recharged slowly from distant areas of precipitation. Others are seasonal or intermittent, responding more directly to recent rainfall patterns. Havasu Creek, which flows through the side canyon below Havasupai Village in the western Grand Canyon, is one of the most visually striking spring-fed streams in the American Southwest. Its turquoise color comes from the high concentration of calcium carbonate dissolved in the groundwater that feeds it, which precipitates out of the water as travertine when the water reaches the surface and loses carbon dioxide to the atmosphere. The series of waterfalls and travertine pools that Havasu Creek creates as it descends toward the Colorado River has been an important landscape feature for the Havasupai people for centuries, and the creek continues to be central to their community today. The movement of groundwater through the canyon's rock formations is slow by human standards. Water that infiltrates the rim today may take decades, or in some cases centuries, to travel through the rock to the point where it finally emerges as a spring. This means that the springs of the Grand Canyon are, in a sense, time-delayed expressions of past precipitation, releasing water that fell as rain or snow years or decades before. Hydrologists studying the Grand Canyon's groundwater system have used chemical tracers, isotopic analysis, and monitoring of water table levels to begin mapping the underground pathways that connect surface infiltration to spring discharge. This research has revealed a system of considerable complexity, with multiple distinct aquifer zones operating at different depths and responding to precipitation on different timescales. Some springs near the river emerge from the deep Muave aquifer, tapping groundwater that has moved through the thick limestone formations deep within the canyon walls over very long periods. Others are fed from shallower systems with more direct connections to recent precipitation. The Redwall Limestone, one of the Grand Canyon's most distinctive formations, is particularly significant as a hydrological unit. This thick, cliff-forming limestone, which weathers to a reddish surface color due to staining from the iron-rich formations above it, is highly susceptible to dissolution by slightly acidic groundwater. Over geological time, the movement of groundwater through the Redwall has created an extensive system of solution cavities, enlarged fractures, and cave passages within the formation, a network of underground spaces that continues to influence how water moves through the canyon's geological system. And it is that network of underground spaces that brings us to the next layer of the canyon's hidden world. The Grand Canyon contains more than 1,000 documented caves. That number surprises most visitors, who come to the canyon thinking primarily of the dramatic landscape visible from the rim and do not consider what might exist within the canyon walls themselves. But the geological conditions that created the Grand Canyon also created an extensive system of natural underground spaces, ranging from small solution pockets barely large enough to shelter a single animal to passages of considerable length and complexity. The primary mechanism behind cave formation in the Grand Canyon is the same process that creates caves in limestone regions around the world: the dissolution of calcium carbonate by slightly acidic groundwater. Rainwater absorbs carbon dioxide from the atmosphere and from the soil, forming a weak carbonic acid that is capable of dissolving limestone over geological time. As acidic groundwater moves through fractures and bedding planes in the limestone, it gradually enlarges those openings, creating solution cavities that can grow over thousands or millions of years into caves of varying size and form. The Redwall Limestone is the primary cave-forming unit in the Grand Canyon, and it is within this formation that most of the canyon's significant cave systems are found. The Redwall is thick, relatively pure in its calcium carbonate content, and extensively fractured, providing both the raw material for dissolution and the network of existing pathways along which groundwater can move and dissolve the rock. Most of the Grand Canyon's caves are inaccessible to the general public and to most researchers. They open onto sheer cliff faces, hundreds of feet above the canyon floor or below the rim, reachable only by technical climbing or rope work. The National Park Service has deliberately not publicized the locations of many of the canyon's caves in order to protect both the caves themselves and the people who might be tempted to attempt dangerous access to them. Among the most significant cave systems in the Grand Canyon region is the Redwall Cavern, located at river level along the Colorado within the canyon. Early river runners described this enormous natural chamber, which opens directly onto the river bank, and Powell himself noted it during his 1869 expedition. The chamber is large enough that some early writers suggested it could seat tens of thousands of people, though that estimate was considerably exaggerated. It is nonetheless an impressive natural space, created by the dissolution and mechanical erosion of the Redwall Limestone at river level. Above river level, cave systems within the Redwall Limestone preserve records of the groundwater conditions that existed when the caves were actively forming, which in many cases predates the canyon's current configuration. Mineral deposits within some of these caves, particularly speleothems such as stalactites and stalagmites, formed from the slow dripping and evaporation of calcium carbonate-bearing water, can be dated using uranium-thorium radiometric methods. These dates tell researchers not only how old the deposits are, but also provide information about past groundwater conditions and, indirectly, about past climate, since the growth of speleothems requires the presence of liquid water moving through the cave. Research on speleothems from caves in the Grand Canyon region has contributed to our understanding of past climate in the American Southwest, providing evidence about periods of wetter and drier conditions over the past several 100,000 years that complements and extends the geological and paleontological record. Some caves in the Grand Canyon have yielded archaeological materials, preserved by the dry and stable conditions of their interiors. Splitwig figurines, small animal figures constructed from split willow twigs in a distinctive technique, have been found in several Grand Canyon caves, sometimes in locations that suggest they were placed there deliberately rather than simply discarded. These figurines have been radiocarbon dated to approximately 3,000 to 4,000 years ago, making them among the oldest documented human artifacts in the Grand Canyon region. Their placement in caves may have had ceremonial significance, though the specific meaning of the practice is not known. The underground spaces of the Grand Canyon are not simply geological curiosities. They are environments in their own right, with their own physical conditions and their own communities of organisms adapted to the specific challenges of life in the dark. Darkness is not the same as emptiness. In the caves and sheltered rock crevices of the Grand Canyon, in the spaces where sunlight has never penetrated, life has found ways to persist. The organisms that live in these environments are not the dramatic megafauna of the canyon's surface, not the condors and bighorn sheep and mule deer that most visitors encounter. They are smaller, quieter, and in many cases remarkable for their ability to survive in conditions that most organisms cannot tolerate. Caves present specific and extreme challenges to life. The absence of sunlight means that photosynthesis, the process by which most surface ecosystems ultimately derive their energy, is not possible underground. Food must either be brought into the cave from outside or generated through chemical processes that do not require light. Water is present in many caves, but not in all. Temperature in deep caves tends to be stable and cool, corresponding roughly to the mean annual surface temperature of the region above. Humidity is often high. Bats are among the most important biological links between the surface world and the cave environment in the Grand Canyon. Several bat species use the canyon's caves as roosting sites, returning from their nightly foraging flights over the canyon and the surrounding plateau, having fed on insects. Their droppings, called guano, accumulate on cave floors and provide a significant nutrient input that supports communities of invertebrates, bacteria, and fungi adapted to processing this organic material. In this way, the productivity of the surface ecosystem, expressed through the insects that bats eat, is transferred into the cave environment through the bats themselves. Beyond the zone reached by bat guano, in the deepest parts of caves where no organic material from the surface penetrates, microbial communities can derive energy from chemical reactions involving minerals in the rock, a process called chemolithotrophy. These microbial communities, which have been documented in caves around the world and in analogous underground environments, represent some of the most remarkable examples of life's ability to exploit energy sources that are not ultimately derived from sunlight. The aquatic environments within the Grand Canyon's underground spaces, the groundwater itself, and the springs where it emerges at the surface, support their own distinctive biological communities. Certain species of invertebrates, including amphipod crustaceans and various aquatic insects, are found only in specific spring systems within the Grand Canyon and have evolved in isolation from surface populations for long enough to develop distinct characteristics. Some of these species exist nowhere else on Earth, their entire global range confined to a single spring or a small cluster of springs within the canyon. The Kanab amber snail, for example, is a tiny land snail with an extremely limited range within the Grand Canyon region, associated with the moist microhabitats near certain springs. Its distribution makes it extraordinarily vulnerable to any change in the hydrological conditions that maintain those spring environments. The continued flow of the specific springs that support this species depends on the continued recharge of the groundwater system that feeds them, connecting the fate of this small organism to the much larger question of how the canyon's groundwater responds to changes in precipitation on the rim above. The biological communities of the Grand Canyon's underground and spring environments are incompletely known. New species continue to be discovered in the canyon's more remote spring systems, and the microbial diversity of the canyon's underground environments has barely begun to be characterized using modern genetic techniques. The hidden biological world of the Grand Canyon is, in this sense, genuinely still being explored. Life in the canyon's underground spaces is modest in its visible expressions. No forests, no herds of animals, no dramatic ecological spectacles. But it is there, persistent and adapted, occupying every viable niche in a landscape where the conditions for life are extreme. And in the rocks surrounding these living spaces, another kind of record endures, not of living organisms, but of the organisms that lived and died in worlds that no longer exist. Imagine standing on the floor of a warm, shallow sea, looking up through clear tropical water at the light filtering down from the surface above you. The bottom around you is covered in a complex community of organisms: corals, sponges, brachiopods, crinoids, and trilobites moving across the sediment. Fish of early and unfamiliar forms move through the water column. The world is alive with biological activity, a richness of marine life that is characteristic of the shallow, warm, well-oxygenated seas of the Paleozoic era. Now imagine that same seafloor buried under hundreds of feet of subsequent sediment, compressed into limestone over hundreds of millions of years, and eventually exposed by erosion on the walls of a desert canyon in Arizona. That is what the fossils of the Grand Canyon represent. The Redwall Limestone, one of the canyon's most prominent formations, is among its most fossil-rich. Deposited during the Mississippian period, roughly 330 to 350 million years ago, in warm, clear, shallow marine conditions, the Redwall preserves an abundance of marine invertebrate fossils. Crinoids, sometimes called sea lilies, though they are animals rather than plants, are particularly well represented. Their distinctive disc-shaped column segments scattered through the limestone in some sections in extraordinary density. Corals, brachiopods, bryozoans, and mollusks also appear in the Redwall, together painting a detailed picture of the diverse marine community that inhabited this ancient sea. Below the Redwall, the Temple Butte Formation, a Devonian-age limestone deposited roughly 370 million years ago, contains the remains of ancient fish, among the oldest vertebrate fossils in the Grand Canyon. The fish preserved in the Temple Butte are placoderms, an extinct class of armored fish that were among the dominant vertebrates in Devonian seas before the evolution of the bony fish groups that would eventually give rise to most modern fish species. The Cambrian formations near the base of the canyon's sedimentary sequence, particularly the Bright Angel Shale, preserve some of the oldest animal fossils in the canyon, representing the early diversification of complex animal life during the Cambrian period. Trilobite fragments and trace fossils. The burrows and tracks of organisms moving through the ancient seafloor sediment document a world that existed more than 500 million years ago, before the evolution of land plants, before the colonization of the continents by animals, before fish had developed anything resembling a jaw. The non-marine formations of the canyon also yield fossils, though of a different character. The Coconino sandstone, that ancient dune deposit, preserves the trackways of early tetrapods moving across the desert surface. These trace fossils are not the remains of the animals themselves, but the impressions of their feet, preserved in the one-stamp surfaces of ancient dunes, and now readable as evidence of biological activity in an environment that existed more than 270 million years ago. The Hermit Formation preserves plant material from ancient coastal and floodplain environments, fern fronds, and other vegetation that gives a sense of the flora that covered the landscape during the Permian period. Taken together, the fossils of the Grand Canyon span an enormous range of geological time and biological diversity, from the simple traces of Cambrian organisms to the vertebrate remains of Devonian fish, to the complex marine communities of the Mississippian limestone. Each fossil locality is a window into a specific moment in the biological history of this region, a snapshot of life preserved in stone. Paleontologists continue to study the Grand Canyon's fossil record, and new discoveries are still being made in formations that have been studied for over a century. The interpretation of some fossil assemblages continues to be refined as new analytical techniques are applied, and as the fossil record from other regions provides additional context for understanding the environments of the Grand Canyon's geological past. The stone remembers life in extraordinary detail. And long after the ancient seas had retreated and the deserts had come and gone and the canyon itself had begun to form, something new arrived in this landscape, something that the rock record had never seen before in this particular corner of the world: people. The Grand Canyon is often described as one of the great natural wonders of the world, a place so dramatic and so vast that it seems to exist outside of ordinary human experience. But people have been living in and around the Grand Canyon for a very long time, and the relationship between human communities and this landscape is far older and far more complex than the national park system that manages it today. Archaeological evidence documents human presence in the Grand Canyon region reaching back at least 12,000 years, and possibly further into the period immediately following the retreat of the last Ice Age glaciers from the higher elevations of the American Southwest. The earliest evidence of human occupation in the region consists primarily of stone tools, projectile points and scrapers, and cutting implements crafted from locally available stone, found at sites distributed across the canyon rim and in some cases within the canyon itself. The people who left these earliest tools were hunters and gatherers, moving through the landscape in seasonal patterns that followed the availability of game animals and plant resources. The Grand Canyon region, despite its dramatic topography, offered a variety of ecological zones within relatively short distances, from the ponderosa pine forests of the high rim to the desert scrub of the inner canyon, each with its own set of resources available at different times of year. A community that understood how to move through this vertical landscape could access a diversity of food sources across the seasons that no single ecological zone could provide on its own. The splitwig figurines found in the canyon's caves, which we encountered briefly in our discussion of underground spaces, provide a glimpse into the ceremonial life of communities living in the canyon region approximately 3 to 4,000 years ago. These carefully constructed small figures, almost always representing deer or bighorn sheep in form, appear to have been placed in caves deliberately, possibly as part of rituals related to hunting. The precision and care with which they are constructed, using a single split willow twig manipulated into a three-dimensional animal form, demonstrates a level of craft knowledge and intentionality that speaks to a rich cultural life well beyond simple subsistence. By approximately 2,000 years ago, communities in the Grand Canyon region were developing new ways of relating to the landscape. The basket-maker cultures, ancestral to the later Pueblo peoples of the Southwest, were present in the region during this period, occupying rock shelters and open sites, and beginning the long process of integrating maize agriculture into an economy that had previously relied entirely on hunting and gathering. The adoption of farming in an environment as challenging as the Grand Canyon required careful knowledge of where sufficient water and suitable soils could be found to support crops, knowledge that was developed gradually through generations of experimentation. Rock shelters within the canyon walls provided natural protection from the weather and were used as habitation sites and storage locations by multiple communities across a long span of time. The dry conditions within sheltered alcoves have sometimes preserved organic materials, basketry, wooden tools, cordage, and plant remains that would not survive in more exposed settings. These preserved materials offer unusually direct windows into the daily material culture of communities that did not build in stone and therefore left less permanent architectural evidence of their presence. The archaeological record of the Grand Canyon is not concentrated in a few spectacular sites. It is distributed across the landscape in hundreds of smaller sites, the accumulated evidence of generations of people moving through, camping in, farming in, and passing through a landscape they knew intimately. That intimacy, the deep knowledge of specific places, specific water sources, specific seasonal resources, was itself a form of cultural knowledge built over time and transmitted from one generation to the next. The people who inhabited the Grand Canyon over these thousands of years were not simply surviving. They were building a relationship with one of the most complex and demanding landscapes in North America, a relationship that would eventually produce the diverse and sophisticated indigenous cultures that European explorers first encountered in the 16th century. The Grand Canyon is not simply a geological feature. It is a cultural landscape, a place that has been inhabited, named, traversed, farmed, preyed in, and cared for by human communities across thousands of years. Several distinct indigenous nations have deep historical and cultural connections to the Grand Canyon, connections that are not merely historical in the sense of belonging to a distant past, but that continue to shape the lives, identities, and relationships of living communities today. The Havasupai people have lived in and around the Grand Canyon for centuries, and their name in their own language Havasu, Baja, means people of the blue-green water. A name that speaks directly to the landscape of Havasu Creek and its distinctive travertine pools that lies at the heart of their homeland. The Havasupai have occupied the floor of Havasu Canyon, a side canyon of the Grand Canyon, for generations, farming the fertile bottomlands near the creek during the warmer months and moving to the rim during winter to hunt. They are widely considered to be among the longest continuously residing communities in the Grand Canyon region. The relationship between the Havasupai and the land changed dramatically in the late 19th century when the establishment of the Grand Canyon Forest Reserve, and subsequently the national park dramatically reduced the territory to which the Havasupai had access. They were confined to a small reservation on the canyon floor for decades, cut off from the rim lands they had traditionally used for winter hunting and gathering. It was not until 1975 that an act of Congress restored a significant portion of their traditional lands to the Havasupai tribe, recognizing the injustice of the original restriction. Today, the Havasupai Reservation encompasses approximately 188,000 acres and includes both canyon floor and rim territory. The Hualapai people, whose name is often translated as people of the tall pines, have traditional territory along the south rim of the western Grand Canyon and along the Colorado River. The Hualapai maintain the Grand Canyon West Resort and the Skywalk, a glass-bottomed observation platform extending over the canyon, as economic enterprises on their tribal land. But the significance of the canyon to the Hualapai extends far beyond economic development. The Colorado River is known to the Hualapai as Ha-Kamwi, the backbone of the river, and the canyon landscape is embedded in their oral traditions, their ceremonial life, and their understanding of history and identity. The Hopi people, whose villages on the three mesas of northeastern Arizona are among the longest continuously inhabited settlements in North America, maintain deep connections to the Grand Canyon that are expressed in their oral traditions and ceremonial knowledge. The Hopi understand the Grand Canyon's confluence of the Colorado and Little Colorado rivers as Sipapuni, the place through which the ancestors emerged into the present world, a concept that is central to Hopi cosmology and that makes the canyon a landscape of profound spiritual significance. The Hopi have maintained salt pilgrimage traditions to the canyon, traveling to collect salt from mineral deposits near the river in ceremonies that connect living communities to ancestral practice. The southern Paiute communities, including the Kaibab band of Paiute Indians whose traditional territory encompasses the North Rim and surrounding areas, have inhabited the canyon region for centuries. Southern Paiute oral traditions contain detailed knowledge of the canyon's landscape, its water sources, its seasonal resources, and its spiritual geography. The Kaibab Paiute developed sophisticated water management techniques adapted to the demands of the high desert environment of the North Rim, including the use of rock catchments and carefully maintained springs. The Diné or Navajo people also have historical connections to portions of the Greater Grand Canyon region, reflected in place names and in oral traditions that speak of relationships to the canyon landscape that developed over centuries of presence in the surrounding area. What these diverse communities share, despite their distinct languages, cultural traditions, and histories, is an understanding of the Grand Canyon as a living landscape rather than simply a scenic resource. For the communities whose ancestors have known this place for generations, the canyon is not primarily an object of wonder to be observed from a safe distance. It is a homeland, a source of material and spiritual sustenance, a landscape embedded in identity and memory in ways that cannot be reduced to a simple description of scenic beauty. Archaeological evidence, oral traditions, and historical documentation together establish that the Grand Canyon has been a cultural landscape for at least as long as human communities have inhabited the region. Understanding what lies beneath the Grand Canyon requires understanding this human dimension as clearly as it requires understanding the geology. The archaeological record of the Grand Canyon is not a single story. It is an accumulation of thousands of small stories, each one preserved in a fragment of pottery, a scatter of stone tools, a section of crumbled wall, a burned patch of soil where a hearth once burned, a handprint pressed into the plaster of a rock shelter wall. Taken individually, each of these fragments tells us very little. Taken together, across hundreds of documented sites distributed through the canyon and along its rims, they begin to reveal the outlines of a human presence that spans thousands of years and encompasses considerable cultural complexity. Archaeologists working in the Grand Canyon region have documented more than 4,000 archaeological sites within the boundaries of Grand Canyon National Park alone. That number continues to grow as survey work reaches areas that have not previously been systematically examined. The distribution of these sites across the landscape tells its own story, concentrating in areas near water sources, along travel routes through the canyon, at the edges of agricultural terraces, and within the sheltered alcoves that provided protection from the elements. Pottery is among the most valuable and abundant materials that archaeologists find in sites associated with later prehistoric communities in the Southwest. Ceramic vessels were used for cooking, storage, and the transport of water and food, and they were produced in enormous quantities by communities that had developed this technology over many generations. The style of pottery, the particular combination of clay preparation, construction technique, surface treatment, and painted decoration, varied from region to region and changed over time in ways that archaeologists have carefully documented, creating a framework for understanding when and by whom particular sites were occupied. In the Grand Canyon, ceramic assemblages from different sites reflect a complex history of occupation by communities from multiple cultural traditions. Tusayan gray ware, associated with ancestral Pueblo communities from the region to the north and east of the canyon, appears widely across the south rim and within the canyon. Kohanina ceramics, associated with a cultural tradition specific to the Plateau region south and west of the canyon, appear in different areas. The presence of these distinct ceramic traditions, sometimes found together at the same sites, reflects the canyon's position at the intersection of multiple cultural regions, a landscape that was traversed and inhabited by communities maintaining connections to traditions centered elsewhere. Basketry, when preserved, provides exceptionally direct evidence of technical knowledge and aesthetic sensibility. The dry conditions within rock shelters have preserved basketry fragments from various periods in the Grand Canyon's archaeological record, including examples from the basket maker period that demonstrate sophisticated weaving techniques and complex geometric designs. These objects were not simply utilitarian containers. They required considerable skill and time to produce, and the patterns woven into them likely carried symbolic meanings within the communities that made and used them. Agricultural features in the Grand Canyon represent some of the most ambitious human engineering in the region's archaeological record. Rock alignments and check dams built across small drainages to slow runoff and allow soil and moisture to accumulate behind them have been documented at multiple locations on the canyon's inner platforms, the broad terraces that step down from the rim toward the river. These agricultural features demonstrate that communities were not simply moving through the canyon in search of wild resources, but were actively modifying the landscape to support crop production in an environment where suitable agricultural land was extremely limited. Rock art, images and symbols created on rock surfaces by pecking, incising, or painting is distributed across the Grand Canyon landscape in ways that reflect long periods of human use and diverse cultural traditions. Petroglyphs, images created by removing the dark surface coating of rock to reveal lighter rock beneath, appear at numerous locations within the canyon, depicting animals, human figures, geometric designs, and symbols whose specific meanings are not always recoverable from the archaeological record alone. Some rock art locations may have served as territorial markers, others as records of significant events or ceremonial activities, others as components of astronomical observation systems. What archaeology cannot do is fully reconstruct the experience of living in this landscape. The knowledge that existed in the minds of the people who made these tools and pots and structures, the conversations that happened around the hearths, the ceremonies that were performed in the canyon's alcoves and open plazas, the names by which specific springs and viewpoints and travel routes were known. That knowledge was held in human memory and transmitted through living oral tradition. The parts of it that have survived to the present exist in the living cultural traditions of the indigenous communities whose ancestors occupied these sites. The material record and the living cultural traditions together provide a more complete picture than either can offer alone. And it is that combined picture that reveals the Grand Canyon not as an empty wilderness where a few scattered ancient people occasionally camped, but as a deeply known and actively managed cultural landscape inhabited across an enormous span of human time. Beyond the ancient and indigenous history of the canyon, another layer of human engagement with this landscape began to accumulate in the 19th century. As explorers from outside, the region encountered the Grand Canyon for the first time and began the long work of trying to understand it on its own geological and scientific terms. The Grand Canyon was not unknown to the outside world before the 19th century. Spanish explorers had encountered it in the 16th century, and their accounts reached European readers in fragmentary form. In 1540, a detachment of soldiers from Francisco Vázquez de Coronado's expedition, led by Garcia López de Cárdenas, became the first Europeans known to have stood on the rim of the Grand Canyon and looked down into it. Their reaction, as recorded by the expedition's chronicler Pedro de Castañeda, was one of frustrated astonishment. They could see the Colorado River far below, and they spent 3 days attempting to find a route down to it before giving up. The canyon's walls appeared much closer from the rim than they actually were, and the river, which looked like a narrow stream from above, turned out to be much wider when the partial descent was finally attempted. Cárdenas and his men withdrew without reaching the river, and the Spanish colonial administration showed little subsequent interest in the canyon. It lay in a region that offered no obvious mineral wealth and was surrounded by terrain that was difficult to supply and govern. For more than 2 centuries after the Cárdenas expedition, the Grand Canyon received little attention from European or colonial American sources, though it remained, of course, well known to the indigenous communities that had inhabited its surroundings for generations. It was not until the mid-19th century that sustained American exploration of the Grand Canyon region began. Lieutenant Joseph Ives of the United States Army Corps of Topographical Engineers led an expedition up the Colorado River by steamboat in 1857 and 1858, reaching the lower canyon and making a partial overland exploration of its rim. His report on the expedition, published in 1861, contained a famous passage in which he suggested that the region was altogether valueless, and that aside from the members of his own party, no tourist would ever visit the locality. He was, of course, wrong on both counts, but his observation reflects the genuine difficulty of the terrain and the challenge of understanding a landscape so unlike anything in the experience of most 19th century Americans. The figure who did more than anyone else to establish the Grand Canyon in the American scientific and public imagination was John Wesley Powell, a one-armed Civil War veteran and self-taught geologist who led 2 river expeditions through the canyon in 1869 and 1871. Powell's first expedition, conducted with a party of 9 men in 4 wooden boats, was a journey of extraordinary difficulty and genuine danger. The party had no reliable maps of the river, no knowledge of what lay ahead, and no way to communicate with the outside world. Several of the original members of the expedition left the party before its completion, climbing out of the canyon rather than continuing downstream. Powell's journals from the expedition communicate something of what it felt like to travel through the canyon in those circumstances: the alternating grandeur and terror of the river, the overwhelming scale of the walls, the extraordinary variety of rock and color visible as the party descended through the geological layers. But Powell was also observing scientifically, recording the rock formations, estimating the age of the geological features he was seeing, forming the interpretations that would eventually contribute to a foundational understanding of the canyon's geological structure. Powell's second expedition in 1871 and and 1872 was better equipped and more methodical in its scientific documentation. Photographs were taken, survey measurements were made, and the data collected contributed directly to the geological reports that Powell subsequently published through the newly established United States Geological Survey, which he would eventually lead. Powell's geological interpretations were not always correct by the standards of modern science, and the understanding of the canyon's geology that he established has been revised and refined many times in the century and a half since his expeditions. But he established the framework for serious scientific inquiry into the Grand Canyon, and the questions he raised about how such a canyon could form, how old its rocks were, and what processes had shaped it continue to drive research today. The expeditions of Powell and those who followed him transformed the Grand Canyon from a regional curiosity known primarily to the indigenous communities living near it, and to a small number of explorers and prospectors, into a subject of systematic scientific investigation, and eventually into a landscape recognized as one of the great natural archives of Earth's geological history. That recognition did not come all at once. It developed gradually as successive generations of geologists, ecologists, archaeologists, and other scientists brought new questions and new tools to the study of the canyon. In the decades following Powell's expeditions, the Grand Canyon became one of the most intensively studied geological landscapes in the world. The United States Geological Survey, established in 1879, sent a succession of geologists to study the canyon's rock formations, map its structure, and interpret its geological history. Charles Dutton, one of Powell's colleagues, produced a landmark geological monograph on the canyon in 1882 that remains a foundational document in the scientific literature on the region. Dutton's work combined rigorous geological observation with a quality of descriptive writing unusual in scientific reports. His accounts of the canyon's visual character and geological complexity helping to communicate its significance to a broader audience than purely technical publications typically reached. The fundamental challenge for early geologists studying the Grand Canyon was the sheer complexity of what they were looking at. The canyon exposed an enormous thickness of rock spanning hundreds of millions of years of geological time. And making sense of that record required not only identifying and naming the individual rock formations, but understanding the environments in which they had been deposited and the processes that had subsequently deformed and eroded them. Stratigraphy, the study of rock layers as a record of time, provided the primary framework for this work. Geologists working in the canyon traced individual formations across the canyon walls, noting changes in their thickness and composition from place to place that reflected variations in the depositional environments in which they formed. The careful documentation of each formation, its physical characteristics, its fossil content, its relationships to the formations above and below it, built up over decades into a detailed stratigraphic framework for the canyon that allowed increasingly precise interpretation of its geological history. The development of radiometric dating in the early 20th century transformed geological research at the Grand Canyon as it transformed geology more broadly. Before radiometric dating, the ages assigned to rock formations were relative ages, based on the fossil content of the rocks and their position in the stratigraphic sequence, but not tied to specific numerical dates. The discovery that radioactive isotopes decay at predictable rates, and that the ratio of parent isotopes to decay products in a mineral could be used to calculate the time elapsed since the mineral crystallized, provided a way to attach numerical ages to the geological record for the first time. For the Grand Canyon, radiometric dating provided crucial information about the ages of its geological formations, particularly its oldest rocks. The Vishnu Basement Rocks, which had been recognized as ancient on the basis of their metamorphic character and their position at the base of the stratigraphic sequence, were assigned numerical ages of approximately 1.7 to 1.8 billion years through uranium lead and other radiometric methods. This dating confirmed their extraordinary antiquity and placed them in the context of the global geological record in a way that was not previously possible. The question of when the canyon itself formed proved more resistant to straightforward dating, because the canyon is primarily a product of erosion rather than deposition, and erosion does not leave behind the kinds of datable minerals that allow direct radiometric dating. Geologists instead had to use indirect methods, dating the volcanic rocks that had occasionally flowed into the canyon and been partially eroded by the river to establish minimum ages for the canyon's depth at those locations, and using thermochronological methods to track the history of rock exhumation. The progressive bringing of deep rocks toward the surface by erosion over geological time. These indirect approaches have generated the ongoing scientific debate about the canyon's age that we noted in our chapter on canyon formation. The debate reflects both the genuine complexity of the geological evidence and the continual refinement of the analytical methods available to researchers. It is a healthy scientific disagreement driven by real evidence and conducted through the normal processes of peer-reviewed publication and scientific discussion. Alongside geological research, systematic archaeological survey of the canyon began in earnest in the early 20th century. The establishment of Grand Canyon National Park in 1919 created an institutional framework for the protection and study of both the canyon's geological and cultural heritage. Archaeological survey work, initially conducted by researchers from institutions including the Museum of Northern Arizona in Flagstaff, and later expanded through the park's own Cultural Resources Program, gradually built up the inventory of archaeological sites that now documents thousands of years of human presence in the canyon. Each generation of scientific inquiry has added new layers of understanding to the Grand Canyon's story, and each new layer has revealed additional questions that the previous generation had not known to ask. That process of progressive discovery continues today, driven by tools and technologies that Powell and Dutton could not have imagined. In the early morning hours, before the canyon fills with the light and the sound of the day, A research aircraft might pass over the rim, carrying instruments that see the landscape in ways that human eyes cannot. Modern remote sensing technology has transformed what scientists can observe about the Grand Canyon without ever setting foot on the canyon floor. Airborne LiDAR surveys, similar to those we encountered in our discussion of North American archaeology, can produce detailed three-dimensional maps of the canyon's topography at resolutions far beyond what traditional surveying methods could achieve. These maps reveal subtle features of the canyon's structure, small fault scarps, ancient landslide deposits, the precise geometry of erosional surfaces that are difficult or impossible to document from the ground. Multispectral and hyperspectral imaging, which captures reflected light across a much broader range of wavelengths than the human eye can detect, allows researchers to map the distribution of different rock types and minerals across the canyon's walls from the air. Different minerals reflect different wavelengths of light in characteristic ways, and a skilled interpreter working with hyperspectral data can identify geological formations and track their distribution across terrain that might require weeks of ground-level work to survey in equivalent detail. Digital elevation models derived from LiDAR data and from satellite-based radar systems have made it possible to analyze the Grand Canyon's topography quantitatively in ways that support sophisticated mathematical modeling of erosion processes. By comparing detailed elevation data collected at different times, researchers can in some cases measure actual erosion occurring in specific parts of the canyon, tracking the ongoing work of the river and the weathering of the canyon walls in real time. Satellite-based gravity measurements have revealed information about the density structure of the rock beneath the canyon, providing constraints on the geological structure of the deeper crust that surface geology alone cannot fully characterize. Subtle variations in the gravitational field across the canyon region reflect differences in the density of the underlying rock, information that helps geologists understand the tectonic framework within which the canyon formed. In hydrology, the installation of monitoring networks of groundwater wells, stream gauges, and weather stations across the canyon region has made it possible to track the movement of water through the canyon's hydrological system in near real time. Researchers can observe how groundwater levels in different aquifers respond to precipitation events on the rim, how spring discharge rates vary through the year, and between years of different rainfall totals, and how the Colorado River's flow regime responds to both natural variability and the operation of the upstream dam system. Isotopic analysis of spring water, using the ratios of stable isotopes of hydrogen and oxygen as tracers, allows researchers to identify where the water feeding specific springs originated and roughly how long ago it infiltrated the surface. Water that infiltrated the rim relatively recently carries a different isotopic signature than water that entered the groundwater system decades or centuries ago under different climate conditions. These isotopic fingerprints help researchers map the underground pathways that connect surface infiltration to spring discharge in the complex hydrogeological system beneath the canyon. Seismic monitoring networks detect and record the small earthquakes that occur regularly in the Grand Canyon region, reflecting the ongoing tectonic activity of the Colorado Plateau and its margins. Analysis of these seismic signals reveals information about the structure of the rock beneath the canyon's surface, using the varying speeds at which seismic waves travel through different rock types to image the subsurface in a technique called seismic tomography. In archaeology, ground-penetrating radar surveys have been conducted at specific sites within the canyon to locate buried features without excavation, allowing researchers to assess the extent and preservation of archaeological deposits before committing to the costly and irreversible process of excavation. Portable X-ray fluorescence analyzers can now be used in the field to determine the chemical composition of stone tools, helping researchers identify the geological sources of the raw materials used by ancient toolmakers and thereby trace the movements of people and materials across the landscape. Ancient DNA extracted from archaeological materials, including human remains, plant materials, and faunal remains preserved in the canyon's rock shelters, is beginning to provide new information about the genetic identity of ancient populations, the plant species they cultivated or managed, and the animals they hunted and kept. These genetic data complement the material record of the canyon's archaeological sites in ways that were simply not possible a decade ago. With all of these tools at their disposal, modern scientists can see further into the canyon's past and deeper into its physical structure than any previous generation of researchers. And yet, for all of this capability, the Grand Canyon continues to present genuine questions that science has not yet answered. There is a particular kind of intellectual honesty required to sit with an unanswered question without filling the silence with speculation. The Grand Canyon invites that honesty because, for all of its status as one of the most studied geological landscapes on Earth, it still contains genuine mysteries, real scientific questions for which the available evidence does not yet provide clear answers. These are not manufactured mysteries or sensationalized unknowns. They are the natural frontier of scientific knowledge in a landscape of extraordinary complexity. The question of when the Grand Canyon formed remains genuinely unresolved in its details. The broad outlines are established. The Colorado Plateau was uplifted. The Colorado River began cutting downward through the rock. The canyon took shape over millions of years. These are well-supported general conclusions. But the specific timing of the canyon's incision, the question of whether a single integrated canyon formed relatively recently, or whether a complex history involving older valley segments being captured and integrated by the modern river system, accounts for the pattern of evidence, continues to be debated by active researchers. New thermochronological data continue to be published, and the community of geologists who specialize in canyon formation research has not yet reached full consensus. The groundwater system beneath the canyon is imperfectly mapped. While researchers have made significant progress in understanding the major aquifer systems and the general pathways of groundwater movement beneath the canyon. The detailed three-dimensional structure of the underground flow system remains incompletely characterized. The connections between surface infiltration on the rims and specific spring discharge points within the canyon are not fully traced in many cases. The total volume of water stored in the various aquifer systems beneath the canyon is not precisely known. And the ways in which this groundwater system will respond to long-term changes in precipitation patterns driven by climate change are a subject of active research and considerable uncertainty. The full extent of the cave systems within the canyon's limestone formations is not known. While more than 1,000 caves have been documented, the inaccessibility of much of the canyon's cliff face means that systematic survey of all potential cave-bearing areas has never been completed. There are almost certainly cave passages within the Redwall Limestone that have not been entered or documented by modern researchers. The extent to which these undocumented cave systems connect to each other and to the groundwater flow paths beneath the canyon is unknown. In a landscape where even the visible surface has not been exhaustively surveyed, the underground remains genuinely incompletely explored. The complete archaeological story of human occupation of the Grand Canyon region has gaps that current evidence cannot fill. The record of human presence in the canyon over the past 12,000 years is not continuous. There are periods for which the archaeological evidence is sparse, reflecting either actual low population in the region or simply the limitations of current survey coverage. The specific cultural affiliations of some of the canyon's archaeological sites are unclear, as the canyon sits at the intersection of multiple cultural traditions whose boundaries and interactions are not fully understood. The reasons why some areas of the canyon appear to have been more intensively used than others are not always apparent from the current evidence. Paleoclimate reconstruction for the Grand Canyon region, while well advanced compared to many other areas of the Southwest, still contains uncertainties that limit our ability to understand precisely how climate variability affected human communities and ecological systems in the canyon across different time periods. The relationships between regional-scale climate drivers and local conditions within the canyon's complex topography are not fully modeled. And beneath all of these specific questions lies a deeper one that is perhaps the most interesting of all. The canyon preserves a record of Earth history that extends back nearly 2 billion years, and yet that record contains gaps, the unconformities we discussed in our chapter on the oldest stones, representing hundreds of millions of years of missing time. What happened during those missing intervals? What rocks were deposited and then eroded away without leaving a trace in the canyon's geological record? Those missing chapters of the story are, by definition, not available for direct study. They can only be inferred from the character of the rocks that bracket the gaps, a reminder that even the most complete-seeming geological archive is in some ways a series of fragments, separated by silences that cannot be entirely recovered. The Grand Canyon's unanswered questions are not signs of scientific failure. They are signs of scientific vitality, of a field of inquiry that continues to generate new observations, new interpretations, and new debates. They are also an honest acknowledgement that the canyon is genuinely more complex than any current model fully captures. Alongside these genuine scientific questions, the Grand Canyon has also generated a different kind of mystery, the kind that lives not in geological reports and archaeological surveys, but in popular imagination and on the internet. That other kind of mystery deserves its own careful examination. Every famous and mysterious-seeming landscape eventually accumulates a layer of legend, misinformation, and wishful speculation on top of its actual history. The Grand Canyon is no exception. Among the most persistent popular myths associated with the Grand Canyon is a story that traces its origins to a newspaper article published in the Arizona Gazette on April 5, 1909. The article claimed that a Smithsonian Institution archaeologist named G.E. Kincaid had discovered a vast underground city within the canyon, complete with Egyptian-style artifacts, hieroglyphics, and mummies stored in elaborate chambers carved into the cliff face. The article described a network of tunnels extending hundreds of feet into the canyon wall, containing artifacts suggesting connections to ancient Egypt or possibly to the lost continent of Atlantis. The story has been repeated and elaborated on the internet for decades, sometimes presented as evidence of a government cover-up, sometimes as proof of ancient Egyptian presence in North America, sometimes as support for various theories about lost civilizations or extraterrestrial contact. There is no credible evidence supporting any aspect of this story. The Smithsonian Institution has no record of anyone named G.E. Kincaid on its staff during the relevant period. No archaeological evidence of Egyptian artifacts, hieroglyphic inscriptions, or an underground city has ever been documented in the Grand Canyon by any credible researcher. The geological structure of the canyon does not contain artificial chambers of the kind described in the original article. Archaeologists and geologists who have worked in the canyon for generations have found no trace of the features the 1909 article described. The Arizona Gazette article was almost certainly a fabrication, the kind of sensational story that newspapers of the early 20th century occasionally published without the fact-checking standards that would be expected today. Its persistence in popular culture reflects not any underlying historical truth, but rather the powerful appeal of the idea that something dramatic and hidden lies beneath a landscape as visually dramatic as the Grand Canyon. The real lesson of this particular myth is not about hidden civilizations. It is about the importance of asking basic questions about the sources of historical claims. Who made this observation? What evidence do they provide? Can the evidence be independently verified? Has any credible researcher been able to reproduce the finding? When a claim fails these basic tests, as the 1909 Canyon City story does at every point, that failure is itself informative. A different kind of popular mythology surrounds the canyon's role in various alternative geological theories. The Grand Canyon's rock formations have occasionally been cited by proponents of non-mainstream geological views, including some who argue for a very young Earth on the basis of religious interpretation. The geological evidence for the great age of the canyon's rocks, established through multiple independent radiometric dating methods and consistent with the broader framework of geology, paleontology, and physics, is robust. The scientific community's understanding of the canyon's geological history is not a matter of ongoing fundamental debate, though specific questions about timing and process, as we have seen, remain active areas of inquiry. Sometimes the real story beneath a landscape is so rich and so strange, involving ancient seas and vanished deserts and underground rivers and thousands of years of human habitation, that the myths people construct around it seem pale by comparison. The Grand Canyon is precisely such a place. The actual evidence of what lies within and beneath it is more remarkable than the legends that have grown up around it. The question now is not what myths say about the canyon, but what the sum of genuine knowledge, geological, hydrological, biological, archaeological, and indigenous, reveals about what this landscape actually is. Stand at the rim of the Grand Canyon on a quiet evening, after most of the day visitors have returned to their cars and the tour buses have pulled away, and the canyon begins to reveal something that the crowds make difficult to perceive. The light changes first. The afternoon sun, moving toward the western horizon, no longer falls directly into the canyon, but strikes the upper walls at a low angle, throwing the ledges and buttresses into sharp relief and turning the rock in colors that shift from gold to amber to deep red as the minutes pass. The shadows in the canyon's depths deepen and pool, the river disappearing from view long before the light fades from the rim. The air cools rapidly, as desert air always does when the sun falls, and the wind that moves along the rim carries the smell of pinyon pine and the faint mineral scent of heated rock, releasing the day's warmth. In that particular evening light, the canyon's layers are visible with unusual clarity, each formation distinct from those above and below it, the whole sequence readable as the geological archive it actually is. The Kaibab limestone of the rim, pale and fossil-bearing, deposited in a Permian sea. Below it the Toroeep, and below that the white band of the Coconino, its cross-bedded structure visible even from the rim on a clear day, the record of an ancient dune desert preserved in its sweeping internal geometry. The Red Hermit Formation below the Coconino, then the complex sequence of the Supai Group, then the sheer vertical face of the Redwall Limestone, that great cave-bearing formation through which groundwater has been moving for millions of years. Below the Redwall, the Muev and the Bright Angel and the Tapats, the marine sequence of the Cambrian, and then, at the bottom of the visible walls and in the depths of the inner gorge, the dark and contorted surface of the Vishnu Basement Rocks, ancient beyond easy comprehension. Every one of those layers is a document. Every one of them records something real about the history of this landscape, about the environments that preceded the canyon, about the processes that deposited and deformed and eventually exposed these rocks. Reading those layers requires knowledge and practice, but the information is genuinely there, preserved in the chemistry and structure and fossil content of the rock itself. Beneath the visible surface of those layers, groundwater is moving. Right now, as the evening deepens, water is percolating downward through the Kaibab limestone. Beneath the rim you are standing on following pathways, determined by the porosity and permeability of successive rock formations, eventually redirected by an impermeable layer and moving laterally until it finds an exit at a spring somewhere in the canyon walls. That water may have fallen as rain months or years or decades ago. It is carrying dissolved minerals from the rock it passes through, gradually enlarging the fractures and solution cavities that it travels along, doing the slow chemical work of cave formation in the limestone formations deep in the canyon wall. In those cave systems, in the dark spaces within the Redwall that human eyes have never seen, mineral formations are slowly growing from the dripping of mineral-laden water. Invertebrate organisms adapted to the dark and the silence inhabit the underground streams and pools. Bats roost in the accessible chambers, flying out at dusk to hunt insects over the canyon rim, carrying the energy of the surface ecosystem underground when they return. The fossils within the rock layers are not passive remnants. They are active evidence, still yielding information to researchers who know what questions to ask and what methods to apply. A trilobite fragment in the Bright Angel Shale carries information about the chemistry of the Cambrian Sea in which it lived, about the temperature and depth and oxygen content of that ancient water, about the evolutionary relationships between the organism that produced it and other organisms of its time. A trace fossil in the Coconino records the actual movement of an actual animal across an actual dune surface more than 270 million years ago, a moment in time preserved with a specificity that still carries the capacity to astonish. The archaeological sites distributed across the canyon landscape are not simply remnants. They are the physical expressions of thousands of years of human knowledge and human relationship with this place. The check dams built across small drainages on the inner canyon terraces represent the accumulated agricultural knowledge of communities who understood precisely where water would collect after a rain and how the soil behind a carefully placed rock alignment would hold moisture through the growing season. The split-twig figurines placed in limestone caves represent the ceremonial life of communities whose relationship to the animals of the canyon was not simply predatory, but was understood within a framework of reciprocal obligation and spiritual attention. The indigenous nations, whose communities have maintained continuous connections to the Grand Canyon across centuries of extraordinary historical pressure, represent the living expression of a relationship with this landscape that reaches back far beyond the historical record. Their oral traditions preserve knowledge of the canyon's water sources, its seasonal resources, its spiritual geography, and its human history that complements and in some ways exceeds what the archaeological and geological record can provide. Their continued presence in and around the canyon is not a footnote to the canyon's history. It is a central part of it. The explorers who first brought the canyon to the attention of the broader scientific world, Powell and his colleagues, the geological survey teams of the late 19th century, the archaeologists of the early 20th, were not discovering a place that had been unknown. They were encountering a landscape that was already deeply known by the communities who had lived within it for generations, and they were beginning the long process of translating that landscape into the frameworks of Western science. The translation was imperfect and incomplete, as translations always are, and it has been revised and refined many times since. Modern science, with its satellite imagery and its geophysical surveys and its ancient DNA analysis and its thermochronological dating methods, can see aspects of the canyon that no previous generation of researchers could access. And yet the canyon's story is still not fully told. The questions that remain genuinely unanswered about the timing of the canyon's formation, about the full extent of its underground spaces, about the complete archaeological history of its human occupation, are not embarrassments. They are the honest frontier of knowledge in a landscape that has proven, again and again, to be more complex than any single generation of inquiry has been able to fully resolve. What the canyon really contains beneath its visible surface is not a single secret. It is layer after layer of genuine complexity, geological, hydrological, biological, archaeological, and cultural, each layer intersecting with the others in ways that make simple summary impossible and sustained inquiry endlessly rewarding. The canyon we thought we knew, the scenic viewpoint, the tourist destination, the famous photograph, was always only the surface of something much deeper. And in the evening light, as the colors shift on the canyon walls and the first stars appear above the darkening rim, the depth of that deeper story becomes, for a moment, almost perceptible. The canyon is quietest just before dawn. The night wind that moves along the rim through the dark hours has stilled. The river, far below, carries on its constant movement without the daytime sounds that humans bring to the canyon edge. The rock walls hold the cold of the night, releasing the heat they absorbed during the previous day so slowly that even in summer the pre-dawn canyon feels cool, the air carrying the particular stillness that comes when the world pauses between darkness and light. In those quiet hours, the canyon is simply itself, not a scenic attraction, not a geological textbook, not a question waiting to be answered. Simply a canyon, a mile deep and miles wide, carved by water and time through an enormous thickness of ancient rock, holding within its walls the record of nearly 2 billion years of Earth's history. The Colorado River moves through the darkness at the canyon's base, as it has moved for millions of years, carrying its sediment, eroding its channel, doing the slow and patient work of deepening the gorge that contains it. The river does not know it is carving a canyon. It knows only the logic of water finding its way downhill, following the gradient that geology and gravity have laid out before it, moving steadily toward the sea. The rock walls stand in the darkness, as they have stood through ice ages and warm periods, through the rise and fall of the sea levels that once covered them, through the long ages of erosion that brought them to the surface from the depths where they formed. The Vishnu Basement Rocks in the inner gorge are as old as they were 1.5 billion years ago, unchanged by the passing of human time. The Redwall Limestone on the rim still contains the shells and traces of the Permian sea creatures that built it, their preserved forms as patient as the rock that holds them. Somewhere in the walls of the canyon, in a limestone cave that no human eye has entered, a stalactite is growing. A single drop of water, carrying dissolved calcium carbonate leached from the rock above, hangs at the tip of the formation and slowly deposits a microscopic layer of mineral before falling into the darkness below. In 1,000 years, that stalactite will be marginally longer. In 10,000 years, it will have grown by a small but measurable amount. The cave keeps its own calendar, measured in mineral deposits rather than days. Somewhere in the canyon's groundwater, water that fell as snow on the north rim perhaps 50 years ago, is still moving slowly through the rock, following pathways through the Muav limestone toward a spring that will eventually release it back into the light. That water has been in the dark for half a century. It carries the chemical memory of every rock surface it has touched along the way. Somewhere in the dry interior of a rock shelter high on the canyon wall, a fragment of ancient basketry rests in the dark, preserved by the same dry air that has protected it for perhaps 1,000 years. The hands that wove it are long gone. The community that used it is gone in its specific historical form, though its descendants continue to live and work and maintain their cultures in the communities around the canyon today. The basket remains, quietly holding its small piece of the human story in the canyon's dry and patient dark. Above the canyon, the stars are extraordinary. Far from city lights, in the high desert air of the Colorado Plateau, the night sky above the Grand Canyon shows more stars than most people in modern America ever see. The Milky Way stretches across the darkness in its river of light, the same river of stars that the Hopi and the Southern Paiute and the Havasupai and all the communities before them have looked up at from this canyon rim across the generations. The stars have not changed. The canyon below them has not changed in any way that a human lifetime would notice. The river moves, the rock stands, the water travels slowly through the stone. What really lies beneath the Grand Canyon? It is a question that opens rather than closes the more carefully you consider it. Beneath the visible canyon lies the geological archive of nearly 2 billion years of Earth's history, written in rock and preserved in fossil and chemical trace, and the physical structures of ancient environments. Beneath the surface rock lies a living hydrological system, moving water through stone along pathways that took millions of years to develop, emerging as springs that have sustained life in a desert landscape across all of human time in this region. Beneath the canyon's walls lie natural underground spaces, some explored and some not, inhabited by organisms adapted to darkness and sustained by the slow transfer of energy from the surface world. Beneath all of that lies the human story, 12,000 years and more of people knowing this landscape, learning its water sources and its seasonal resources and its spiritual geography, building their lives within it and their understanding of the world around it. The rock shelters and the check dams and the pottery fragments, and the split-twig figurines, and the rock art, and the oral traditions of living communities are all part of what lies beneath the surface of the canyon we see from the rim. And beneath all of that lies the thing that is perhaps hardest to hold in mind and most important to try to understand. Time. An amount of time so large that it makes the entire span of recorded human history seem like a single breath. An amount of time in which seas advanced and retreated across this landscape dozens of times, in which the continent moved thousands of miles northward, in which species evolved and flourished and went extinct and were succeeded by new forms of life, in which mountains rose and were completely eroded away before the current canyon even began to form. The Grand Canyon is an archive of that time, the most complete and most legible archive of Earth's deep history that exists anywhere on the surface of the planet. And like all archives, it rewards patience. It rewards the willingness to sit with a question longer than is comfortable, to resist the impulse to fill silence with easy answers, to allow the complexity of the record to speak at its own pace. The canyon has been keeping its record for a very long time. It will continue keeping it long after the questions we are currently asking have been replaced by better questions that we have not yet thought to ask. The river moves through the darkness at the canyon's base. The rock stands patient in the night. The water travels slowly through the stone. The stars continue their quiet passage overhead. And somewhere beneath all of it, in the oldest and deepest part of the canyon's geological record, in rock that was ancient before the first fish ever swam in Earth's seas, the planet continues the slow and indifferent work of being itself. The canyon does not need us to understand it, but understanding it, even partially, even imperfectly, is one of the more remarkable things that human beings are capable of doing. Rest now. Let the canyon hold its silence through the night. Let the river carry its sound through the dark. Let the ancient rock stand in the cold air beneath the stars. The story of what really lies beneath the Grand Canyon is not finished. It will not be finished in our lifetimes or in the lifetimes of those who come after us. But tonight, we have followed it as far as the evidence and the evening will take us, and that is enough. The canyon waits in the dark, as it has always waited, patient beyond any human measure of patience, holding its record of vanished seas and ancient deserts and living rivers and hidden water and the long human story of knowing this place. The water moves through the stone. The stars move slowly overhead. The canyon breathes the night air, and the world, for this moment, is very quiet. This has been what really lies beneath the Grand Canyon, a History Sleepy Time documentary. Thank you for spending this time in the ancient landscape of the canyon, moving slowly through its geological history, its hidden water, its underground spaces, its fossils, its human stories, and its unanswered questions. If this documentary brought you peace and curiosity, consider subscribing to History Sleepy Time, where quiet journeys through America's landscapes and histories are always waiting for you. Good night.